Hi everyone, in this video we're going to talk about measures of dispersion. So measures of central tendency describe the typical value of a variable. We talked about mean, median, and mode last time. Dispersion is the degree to which the data are spread out. So let's take a look at this example. This table here represents the IQ scores of a random sample of 100 students from 2 different universities. So for each of the 2 universities, we're going to compute the mean IQ score and then draw a histogram using a lower class limit of 55 and for the first class and a class width of 15. So we can enter the data into StatCrunch and then we will determine that the mean or average IQ for both universities is actually 100. But as you can see from the histograms for each university, the data is spread out very differently. So even though both universities have the same mean IQ, the histogram suggests that the IQs from University A are more spread out or more dispersed. Though the IQ of 100 is typical for both schools, it appears to be a more reliable description of the typical student at University B, and that's because most of the students have an IQ score closer to that mean of 100 at University B as opposed to University A where it's more spread out. So the higher proportion of students from University B have IQ scores within, we can say, 10 points of the mean, which is of 100, compared to University A students. So let's determine the range of a variable from raw data. The range R of a variable is just the difference between the largest data value and the smallest data value. So to get the range, we just subtract largest minus smallest value. The data in this table represents the first exam scores for 10 students in a stats class, and we're going to compute the range. So if we identify the highest score at 94 and the lowest score at 62, then the range is the difference between those, so we get 32. And so the difference between the best score and the worst score was 32 points. Now let's determine the standard deviation. So the standard deviation is based off the deviation about the mean. So how far the values in the data set deviate or are spread out from the mean value. The popular standard deviation, so this is going to sound very mathy, but we'll go through it, of a variable is the square root of the sum of squared deviations about the population mean, and then we divide that by the number of observations, and then the other way to say that is it's the square root of the mean of squared deviations about the population mean. So let's look at that. The population standard deviation is symbolically represented by this Greek symbol here. This is lowercase sigma. And so here's the formula. So notice it's the square root of, and what you're doing here is you're taking the sum, you're adding all of these differences, which we're calling the deviation about the mean. So this is your one data point minus the mean, mu. And so it's just the difference between that value, that observation value, and the average. And we just do that for all of the data points. We square those differences, add them, and then divide by the population size. And then once we take the square root, that is what we call our standard deviation. Okay, so Formula 1 is conceptual because it actually, like we just talked about, sort of breaks down how the formula works. And so there's another way to compute this, and we call this a computational formula because it's much easier to work with. And so it's still a square root, but what you do is you take 2 different summations. And so in this one here, notice what you're summing. You're taking the summation of the squares of each of the data points. So you're squaring them first, then you're taking the sum. Over here, you're taking the sum, so you're adding up all your data points, then you're squaring that answer. Okay, and then that number is going to get divided by n, You subtract those two values and then divide the whole thing by n, and then make sure you take the square root. Okay, so let's take a look at this example. We're going to compute the population standard deviation of the test scores. So the first thing we're going to do, column 1, is just list our test scores and then calculate the mean. So if we just add these up, divide by 10, we got that the population mean was a score of 79. So then going through our calculations, what we need for our standard deviation, this third column is the deviation about the mean. So it's just this score minus the mean. How far away is this score from the mean? It's 3 more than the mean. The next one is a score of 77 minus 79. So it's 2 away from the mean. But because it's negative, it's 2 less than the mean. And we do that for each of these scores. These numbers are all how far they are from the mean value. And then a good idea for checking purposes is if you add up these deviations about the mean, you always should get 0. So if you didn't get 0, just check your work. And then in the third column, we have the number we just calculated, the deviation about the mean. We just square it. And remember, when you square, anything that was negative turns positive, because technically you're squaring the negative sign as well. And so notice a couple of things. Everything is positive, and then anything that had a larger deviation about the mean, like for example this negative 17, it gave us a really large squared deviation about the mean. So then we add up all the entries from the fourth column of our work, and then we divide by the population size, which for us was 10. So when we added up all the squares of the deviations about the mean, that was a 946. Population was 10, and so this was 96.4 points, but this is still squared. So our last step is actually to take the square root. And so the standard deviation is 9.8 points. So we can use the other formula and get the same thing. So this is a less work formula because look at the computation. So we have our scores, and part of the formula just says add them. So we add those up and we get 790. The other part of the formula says we have to square those scores, those data points, and add them up. And then we just plug them in these two spots. So right here, this was the sum of the scores, and then we square that. So that's why it's 790 squared. And then the first term here was our scores squared and then added up. That's where that 63,374 came from. And we just do this division, subtraction, and then divide by 10 inside the square root, and we get 9.8 also. So 2 ways to calculate the standard deviation, and more so this version is a little bit easier to work with. So the sample standard deviation is really similar, and what you do, the main difference is what you divide by. So we still take the deviation about the mean. Some of our notation changes though. So we don't use sigma. Sigma is reserved for our population standard deviation. This time we're going to use S. S for sample standard deviation. And so this is still our data point minus the average or the mean. And so it's just the difference between that data point and the mean squared, and then we do that and add those up. And then this time, whatever our sample size is, we divide by 1 less than that, and then take the square root. Okay, so just a caution real quick, be sure to use X bar with as many decimal places as possible to avoid rounding errors. So if you're calculating and you're inputting what X bar equals by like hand, by typing it, instead of using like an exact value, then you want to make sure you use as many decimals as possible. So the computational formula for our sample standard deviation, very similar to our other one. It's just the same thing, but we're dividing by n minus 1 for our sample size. Okay, and then just a caution, make sure you divide by n minus 1. If we're talking about population, you divide by the entire population size, the capital N. But if it's a sample of the population, you always divide by 1 less than that sample size. So just a quick note on degrees of freedom. We call n minus 1 the degrees of freedom because the first n minus 1 observations have freedom to be whatever value they wish, but in order to get to 0, when we add up the deviations about the mean, the nth number in the list, basically, the nth value, can't be any value it wants. It has to be whatever number is required to get 0 when you add up the deviations about the mean. So just a note on calling it degrees of freedom. So we're going to compute the sample standard deviation of the sample of these scores, and we're going to take 4 students with the score 62, 88, 77, and 68. Okay, so we're going to use our conceptual formula. So I have our 4 scores. If you take the mean of this, just add them up, divide by 4, you're going to get 73.75. The deviation about the mean for each one, you just take that value, that score, minus the mean. And then, so just so you remember, this is saying that 62 is 11.75 points lower than the mean value. We check that you get 0 here when you add them up. And then we also need the squared deviations about the mean. So just take the numbers from our third column and square them, and then add those up. All right, so then we sum the entries in column 4, which was there, and then divide by 3 because the sample size was 4 and we divide by 1 less than that. So we're going to divide by 3 and we get 128.25 squared points. Last step is to take the square root. So the standard deviation of our sample was about 11.3 points. So using the computational formula, we do get the same answer. Let's just walk through it real quick. If we add up the data points, that's 295. And in our formula, that number gets squared. And then going back to our table, we square the data points and then add that up. And that's going to go in the front of our formula here. And then we just do our computation, and that's how we got 11.3 also. All right, this time we're going to use some software to do the same thing. We already got our values, but let's just try it out with some technology. So this is what we would get if we use a calculator, and so let me show you that one. Okay, so I input the values on my list for our scores of our test. To do that, I just went to Stat, and then Edit, and then inserted the values. So then I'm going to go to Stat and Calc, and pick one, Variable Stats. And I wanted my second list because I had another one from a different example. But if it was my other list, I just go to Second Lists, and I would go down to the list I want. Okay, then we're going to go down to Calculate, and here it is. So we have our mean here, and then notice what it gives us. With the calculator, it doesn't know if you are dealing with a population or a sample of the population. And so it actually gives you 2 standard deviations, and you basically just have to pick the right one. And so in this case, remember sigma was our population standard deviation, and S was our sample standard deviation. So this was the population. It was all 10 scores, so we want the 9.81. And then if we wanted to do the same thing for our 4 scores, that was our random sample, we would just input those as a different list. Okay, so now let's do it again with Excel. So now I'm in Excel, and I typed in my scores. And so this time I'm going to use the data analysis. So I'm going to go down to descriptive stats. And let me get rid of this and just show you how to do it. So I want to go to my input range, and I'm actually going to highlight the title scores because when I use this tool, it counts that as like a title. So I went and highlighted my input range. My output range is just where it's going to locate it. Let me just put it right here. And I want to check off summary statistics. It's going to give me a lot of information. Okay, so it gave me the mean, 79, and then our standard deviation was 10.34. So if you recall, our standard deviation for the population, this was like 9.8. So this is actually calculating the standard deviation as if this was the sample of the whole. And so what it would do, the difference in the calculation is that it would divide by 9 instead of 10. And so let's see if we can get, let's just put something in here. Let's say that this is sample, let's say S for sample standard deviation. And let's see if we can calculate the standard deviation as a population. So I'm going to say standard deviation P for the population. And let's highlight these values. And there we go. There's that 9.8 number. Okay, so just be careful with that if you're using Excel. It's going to give you the sample size standard deviation if you use the data analysis. Okay, so just a note with the calculator, as we saw with Excel, you just need to be careful about which standard deviation you need because they are different values depending on if you're dealing with a sample or the whole population. And so this case, it's a little bit more clear. Sigma is reserved for the population standard deviation and S is the sample standard deviation. Same thing over here with the 4 scores that we looked at as the sample. So for that one, we would want the one S, which was 11.3. So some interpretations of the standard deviation. We've calculated it. Let's talk about it a little bit. And so standard deviation represents the typical deviation from the mean. So how far, like typically, is a data point from the mean? Like how far away is it? As such, the standard deviation may be used to judge whether a particular observation is far away from the mean of the data set. Like, is it really far away? Is it an outlier, basically? And so if we have a standard deviation value, so right here, this is just an example. So let's say the standard deviation, we calculated and we got 6. And so let's say this mean was 25 for our data. Then the number 31 is a length of 1 standard deviation away from the mean. And then if we had a different mean value, so this is a different example, sorry, a different standard deviation value. Let's say we did our calculation and the standard deviation was 2. Let's still keep the average or the mean at 25. So then a number 27 would be what we call within 1 standard deviation away from the mean. Something further away, like 29, would be within 2 standard deviations of the mean. And then 31 would be 3 standard deviations away from the mean, and so on. So this helps us realize how far away values are from the mean of the data. So a good rule of thumb is to consider an observation far away if it's more than 2 standard deviations from the other observations, such as the mean. So when judging the unusualness of an observation, it's vital that you consider the underlying variation in the data as measured by the standard deviation. So if we're comparing 2 populations, the larger standard deviation means the greater the dispersion, or the spread, like the data is more spread out, of the distribution, provided the variable of interest from the 2 populations has the same unit of measure. So if we have a larger standard deviation, the data is more spread out. So going back to our example with IQ scores from the 2 universities, we now know we could say that using the standard deviation, or we can use the standard deviation to determine whether University A or B has more dispersion in the students' IQ scores. Okay, so you can enter this into Minitab, or you can do it on the calculator or in Excel or on StatCrunch. And so University A and B both had the mean of 100 for the IQ, if you remember. And so our standard deviation for University A is actually 16.8. and then the standard deviation for University B is 8.3. So the sample standard deviation for University A is larger than University B. And so the IQ scores of University A were more dispersed or spread out. And we can tell that visually from the histogram when we looked at it. So next, let's determine the variance. So we just talked about standard deviation. Now we're going to talk about variance of a variable. The variance is just the square of the standard deviation. So the good thing is we already did all the work for standard deviation. Variance is just that value squared. So if it's a population we're talking about, that's sigma squared. If it's a sample, that's just s squared. So we're going to use our result from our population standard deviation for the test scores of 9.8, and then our sample standard deviation from those 4 test scores of 11.3 to determine the population and sample variance of test scores on that exam. Okay, so because our standard deviation of our population was 9.8, we just square it, and 96.04 points is going to be our variance. And then very much similar process. So our sample variance is just our 11.3 squared, so 127.7 square points. So basically, if you're finding standard deviation right before you take the square root, that's what we call the variance. Okay, let's mention this real quick about variance. So whenever a statistic consistently underestimates or overestimates a parameter, it's said to be biased. And so to obtain an unbiased estimate of a population variance, we divide the sum of squared deviations about the sample mean by n minus 1. So we've already been doing this, but just to think about it, if we had divided by n, little n, then we would actually be underestimating the population variance each time. So just to help you think about this real quick, imagine if you worked at a carnival and you were supposed to guess people's weight, but you found out that you kept getting it wrong by underestimating. So what you can do, that's actually a biased estimation because you're constantly underestimating. So what you can do is just increase your estimate each time to account for that. And so that's sort of what's happening here. If we divide by n minus 1 instead of n, it's increasing that number enough for it to hopefully not be biased. Next, let's use the empirical rule to describe data that are bell-shaped. So this is specifically for bell-shaped data. So the empirical rule, if a distribution is roughly bell-shaped, then first, approximately 68% of the data lie within 1 standard deviation of the mean. So that's a lot. About 68% of the data is within plus or minus 1 standard deviation from the mean mu. So this is just what it looks like mathematically. And then approximately 95% of the data lie within 2 standard deviations of the mean. So that's almost all of it. So approximately 95% of the data lie within the mean mu plus or minus 2 standard deviations. And then about 99.7% of the data lie within 3 standard deviations of the mean. And then note, we can also use the empirical rule based on sample data, and then you just replace mu with x bar, and then s with sigma. Okay, so here's a visual for everything that we just said. Notice our distribution of our data is definitely bell-shaped. And so here's the mean, mu, right here in the middle, and 68% of the data is within 1 standard deviation, either above or below that mean value. And so on the horizontal axis here, it's just saying the mean plus 1 standard deviation, the mean minus 1 standard deviation. And then 95% of the data is within 2 standard deviations. Okay, and so there's percentages corresponding to this. So if we just kind of focus on the left or less than the mean, for one standard deviation, that's about 34% of the data. And then 2 standard deviations, that's about 13.5 more percent of the data. And if we add all those up, that's why we get the 95% from. And then if we spread out a little bit further and we do 3 standard deviations, that encompasses 99.7% of all the data are within 3 standard deviations away from the mean. And then we have just this little tiny bit outside of 3 standard deviations, about 0.15%. So to use the empirical rule, let's use it for the university example with the IQ values. So University A, we're going to determine the percentage of students who have an IQ scores within 3 standard deviations of the mean, according to the empirical rule that we just talked about. And then we're going to determine the percentage of students who have IQ scores between these certain values, 67.8 and 132.2, also according to our empirical rule. Then we'll determine the actual percentage of students who have those IQ scores. So real quick, let me explain the difference. Part B is asking us to determine the percentage of students with scores in between these two numbers using the empirical rule. And then part C is asking us to find that same number, but not using the empirical rule. We're going to use actual calculations from our percentages. And then part D says, according to the empirical rule, what percentage of students have an IQ above 132.2? All right. So to use the empirical rule, a histogram must roughly be bell-shaped, and notice that this one is. Okay, so if you recall, we had found that the mean IQ was 100. And so if we just do our standard deviation calculation, we would end up getting 16.1 for our standard deviation. Okay, so we're going to look at this visual to help us out. And so our mean is right here in the middle, 100. And according to the empirical rule, 68% of the data is within one standard deviation from the mean. So we take our standard deviation and we just subtract it from the mean. So 100 minus 16.1. So we get 83.9 on the lower end. And we say 100 plus 16.1. And we get 116.1 on the higher end. So 68% of the IQ scores are between 83.9 and 116.1. And then to get the values that we need for our horizontal axis here, we just keep subtracting multiples of the standard deviation. So to move over 2 standard deviations from the mean, we just say 100 minus 2 times 16.1. That's where 67.8 comes from. We do the same thing but with addition over here on the other side. And then we do this one more time with 3 standard deviations. So 99.7% of the data, or the IQ scores, should be between 51.7 and 148.3 according to the empirical rule. Okay, so we have exactly what I was just saying here, that 99.7% of the scores are between 51.7 and 148.3. Okay, so for question B, it asked what percentage of students had IQ scores between 67.8 and 132.2. And nice enough, those are actually both exact standard deviation values away from our mean. So 67.8 was exactly 2 standard deviations below the mean, and 132.2 was exactly 2 standard deviations above the mean. And so just by the facts of the empirical rule, we know that that means that 95% of the IQ scores were between those numbers. Now, this time we're going to do the same values of 67.8 and 132.2, but we're not going to do just use the empirical rule. We're going to calculate. So of the 100 scores listed in the table, 96% of them are actually between those two numbers. And the way you can do that is to go back to the table, and you'd actually want to either, you can use technology, but find all the scores in between these two, and then take that amount and divide it by 100 to get this percentage. So it was a little bit more work than just looking at the empirical rule, but we can get that value manually and find out that it was actually really close to the empirical rule's approximation. So the last question was asking about how many students about have a score more than 132.2, and because 132.2 was exactly 2 standard deviations away from our mean, we just add up the percentages based on what we know from our empirical rule. So based on the rule, we know that 2.35% are between 2 and 3 standard deviations away from the mean. And then what's left after that is the 0.15%. So we just add those up, and we get about 2.5% of the students have an IQ score above 132.2. The last thing we're going to talk about is using Chebyshev's inequality to describe any set of data. And so what Chebyshev's inequality does is it's for any data set or distribution, it says that at least this number, we'll go through the calculation, of observations lie within this number of standard deviations from the mean. Okay, so basically what it's saying is at least when you choose a number of standard deviations, let's say it's 2, at least 1 minus 1 over 2 squared times 100%, whatever percent that gives us, at least that percentage of the observations lie within 2 standard deviations from the mean. And you can do this for any standard deviation value greater than 1. Okay, so notice that it is an at least. So at least this percentage of the data lies between a certain number of standard deviations from the mean. And so it's going to be a estimate, and usually it tends to be conservative, but sometimes it's actually pretty spot on. So we can also use Chebyshev's inequality based on sample data. So let's just use that real quick on the example we just worked on. So determine the minimum percentage of students who have IQ scores within 3 standard deviations of the mean, and this is going to be according to Chebyshev's inequality. And then we're going to find the minimum percentage of students whose scores are between these two scores that we looked at previously, 67.8 and 132.2, also by using Chebyshev's inequality. And then we'll do it very specifically. We're going to determine the actual percentage of students whose scores are between those numbers, which we already did actually. Okay, so according to Chebyshev's inequality, if we're talking about 3 standard deviations, k is 3. And so we just plug that number into our formula. And so 1 minus 1 over 3 squared times 100%. So that's just 1 minus 1/9 times 100% gives us 88.9%. So what that says is, if you interpret it, it says 88.9% of all students have IQ scores within 3 standard deviations from the mean. And so if you want to get those in scores, because right now it's just saying standard deviations, then we know that the mean was 100. We know that the standard deviation was 16.1. And so we're talking about 3 standard deviations. So we just take our mean minus 3 times our standard deviation. And so our low score end is 51.7. And our high score end, we do the same thing with 100 plus 3 times 16.1. We get 148.3. And so what this is saying, if you'd say it in terms of scores, because that might be a little more meaningful than saying within 3 standard deviations, it's saying at least 88.9% of the students had scores between 51.7 and 148.3. Now, if you remember when we used the empirical rule, according to the empirical rule, we had gotten that 99.7% of the students had scores in between these two. But this is a conservative estimate. It's saying at least. So it's this number or more, 88.9. So 67.8 was exactly 2 standard deviations below the mean. for part B, and then 132.2 is exactly 2 standard deviations above. And so if we use Chebyshev's inequality with k equal to 2, we get 1 minus 1 over 2 squared times 100%, giving us 75%. So what this says, according to Chebyshev's inequality, is that 75% of all the IQ scores lie between 67.8 and 132.2. Now, notice a couple of things. If we compare that to part C, which we had found earlier, that actually 96% of the scores were between those two numbers, Chebyshev's theorem was a conservative estimate. And then if you remember from the empirical rule said 95% of the scores were between those two scores. And so Chebyshev's theorem gives us a good minimum value. All right, that's it for this one. Thanks for watching.